Good morning all, my name is B. Santhosh Kumar, Assistant Professor, Institute of Aeronautical Engineering. My subject is Computer Architecture. Today I am discussing about problem solving on micro operations. So what is micro operation? Micro operations, also known as micro ops, are the functional or automatic and operations of processor. These are low-level instructions used in some designs to implement complex machine instructions. They generally perform operations on data stored in one or more registers. They transfer data between registers or between external buses of the CPU. Also performs arithmetic and logical operations on the registers. So what is micro operation? So there are so many types of micro operations are there. So before going to this micro operations, we have to discuss what is micro operation. So it is the functional operations and it is performed in processor, and they are the low level instructions, that means called machine level languages. Or binary language or binary code. So these are the low level instructions. So instructions means we have to go for add ax comma bx or anything. So we have to go move ax comma bx. So these are the low level instructions, means machine understanding level language or binary instructions, and they generally perform operations on data stored in one or more registers. Suppose I am going for add ax comma bx. So a is one register, b is one register. So in these registers the data will be stored. So it perform operations, anything, what are the operations? In any operations we have to perform the data stored in one or more registers. So when I am going one instruction, that is add ax comma bx, here a is one register and b is another register. So in this register the data is stored, in this b register the data is stored. So multiple registers for using for multiple data for the micro operations, and the transfer of data between the registers or between external buses of the CPU also performs arithmetic and logical operations on the registers. So micro operations are also used in logical operations or in arithmetic operations. Arithmetic operation means we are going for addition, subtraction, multiplication, division, increment, decrement, and so on. In the logical micro operations, we are going for the logic gates. So AND gate, OR gate, XOR, NOR gate, like this. So for these operations, we are using micro operations. So majorly micro operations are dividing as a two types. That is a arithmetic micro operation and logical micro operation. Arithmetic is one type and logical is another type. In executing a program, operation of a computer consists of a sequence of instruction cycles with one machine instruction per cycle. Each instruction cycle is made up of a number of smaller units: fetch, indirect, execute, and interrupt cycles. Each of cycle involves series of steps, each of which involves the processor registers. These steps are referred as micro operations. The prefix micro refers to the fact that each of the step is very simple and accomplish very little. So majorly in the discussing about the micro operations, we are going for the any of the program. We are operating a program in a computer consists of a instruction cycle of one machine instruction per cycle. Okay, one instruction per cycle is possible, and each instruction is made up of a number of smaller units. So fetch from the computer and execute, fetch, execute, and interrupt of a cycle. So the steps are referred as a micro operations. These prefix micro operations are fact that each step is very simple and accomplish a very little. So majorly micro operations is a program execution. So it is a program execution. These are we are dividing as a program executions of three types. Instruction cycle. Okay. So suppose I'm taking here 3 instruction cycles. Every instruction cycle we have fetch, indirect, execute, and interrupt will be there. Fetching is a micro operations, and indirect micro operation, execute and interrupt are the micro operations. Okay, program execution is a instruction cycle, and these instruction cycle we are going for the fetch, indirect, execute, and interrupt. So these are the micro operations. Types of micro operations. Register transfer micro operations. Transfer binary information from one register to another. Arithmetic micro operation. Perform arithmetic operation on numeric data stored in registers. Logical micro operations. Perform bit manipulation operations on data stored in registers. Shift micro operations. Perform shift operations on data stored in registers. So we are dividing as so many types, but majorly we are using arithmetic and logical micro operations. But we will discuss first one, register transfer micro operation. Transfer binary information from one register to another. Suppose I have R1 register with 8-bit data. I have to transfer to another register. Same 8-bit data I have to transfer to another register. Is it possible? It is possible with register transfer micro operations. Next, arithmetic micro operation. Perform arithmetic micro operation on numeric data stored in registers. So already we know that arithmetic micro operations for add, sub, mul, division, increment, decrement, like this. So for these, majorly we are using for these instructions: add, addition operation, subtraction, multiplication, division, increment, and decrement. So majorly these arithmetic operations are using for this one. It perform arithmetic and numeric data stored in registers. Logical micro operations perform bit manipulation operations on data stored in registers. So AND, OR, XOR, XNOR, NOT, like this, XOR. So for logic gates. For the logic operation means when you are performing using the logic gates, performing that is a logic micro operations to perform the bit manipulation operations on data stored in registers. Shift micro operations perform shift operations on data stored in registers. Shift means we are shifting from one register to another, or one memory to another memory, like this. These are the shift micro operations. The first one is a arithmetic micro operation. We will discuss first one, arithmetic micro operation. In general, the arithmetic micro operations deals with the operations performed on numeric data stored in the registers. The basic arithmetic operations are classified in the following categories: addition, subtraction, increment, decrement, and shift operations. So some additional arithmetic micro operations are classified as add with carry, subtract with borrow, transfer, unload, etc. So in the arithmetic micro operations, we will deal with operations performed on numeric data stored. So when I am going for the add ax, bx, so I am using registers with particular data, registers with data. So the basic arithmetic micro operations are classified as the addition. In the micro operation we are called as add, subtraction, sub, increment, inc, decrement, dec, and shift operation, shift left, shift right, like this, shl or shr, shl, shr, shift rotate, like this. Okay, so these are the arithmetic operations. Suppose I am going for the subtraction, sub ax, bx, and some additional arithmetic micro operations are classified as add with carry. I am adding with any carry. Okay, add with carry. Subtract with borrow. If any borrow will be there, we are going for the subtraction. And a transfer or loading operation. Suppose I have 1011. B equal to 1011. Shall we get any carry? Maybe we'll get carry. 1 plus 1, 10, 0, 1 plus 1, 10, 11, 0 plus 0 plus 1, 1 plus 1, 10. So are we getting carry? As it is a 4 bit, but I am getting 5. So it is a add with carry. Okay. For this, like this operations, we are going for add with carry, subtract with borrow, and shift or load operations. And the following are the table shows the symbolic representation of various arithmetic micro operations. Symbolic representation and description. Suppose I am taking two registers R1 plus R2. So addition of these, add R1 comma R2 added to the R3. So the addition of two numbers, the resultant value is stored in R3. That means the content of R1 plus R2 or transferred to R3. Suppose R1 equal to 10, R2 equal to 11. So 10 plus 11, the resultant value is stored in R3 register. 0 plus 11, 1 plus 1. So it is carry we are getting. So the resultant value stored in R3 register. R3 to R1 minus R2. That means subtracting two registers. That means two numbers of subtraction of two numbers. These resultant value is stored in R3. So the content of R1 minus R2 is transferred to R3. R2 tends to R2 bar means complement. Complement of the R2 one's complement. Suppose here I am giving R2 equal to 1. What is about the R2 bar? Equal to 0. So if I am giving the input is R2 equal to 1, but I am getting the R2 bar, R2 complement equal to 0. So input is 1, output is 0. What is it? That means the complement of R2 is 0. This R2 is stored, R2 bar is stored in R2. So R2 bar is stored in R2 like this. And R2 bar plus 1, complement of R2 plus 1. That means after the complement of R2, we are adding plus 1. That is called 2's complement. It is also called 2's complement of R2. That is a negative. And so suppose here R1 equal to 0. What about the R1 bar is equal to 1. So this R1 bar equal to 1. But here complement R1 bar plus 1. That means we are adding 1 plus 1. So 1 0. This resultant value stored in R2. So it is about the R2 bar, that is called 1's complement. R2 bar is nothing but 1's complement. R2 bar plus 1 means that is called 2's complement. So R1 plus R2 bar plus 1. So R1 register, what is the value of R1 and what is the value of R2? We are complementing that value and R2 plus 1. That means it is the 2's complement. R1 value plus 2's complement of R2. Okay, that is the value R1 plus R2 bar plus 1. So R1 plus 2's complement of R2. We are adding both together. And what is the result that will be stored in R3? So R1 plus 1. That means increment of R1. Suppose R1 equal to 1. We are incrementing 1 plus 1 to this one. The resultant value stored in R1. Here decrement. What is the R1 value? For that R1 equal to 1. Decrement means 1 minus 1. That is 0. It will be stored in R1. Okay. So R1 plus incrementing of R1. The resultant value stored in R1. And R1 decrement value. That decrement value stored in R1. So R1 plus R2, addition, subtraction, complement, 2's complement, and addition of R1 plus 2's complement of R2, increment, decrement. So these are the some symbolic rotations and micro operations are performed. So here I am taking one example. Design a 4-bit binary full adder with truth table. Suppose what is a how we are adding 4-bit binary adder I am taking. What is a full adder and what is a truth table of this one we will discuss. Digital circuit that performs arithmetic sum of 2 bits and the previous carry is called full adder. Digital circuit that generates the arithmetic sum of 2 binary numbers and the length is called the binary adder. So full adder means arithmetic sum of 2 bits and the previous carry is called the full adder. So 1 plus 1 example, what is the value? And the previous, is there any carry is adding? Yes, the carry is adding. Suppose I am going for 1 0 1 0 or 1 0 1 1 example. Here also I am taking 1 0 1 1. So 1 plus 1 0 and carries 1 is there. Yes. How many? Here I am adding only 2, that is A plus B example. But here I am adding A 1 2 3 are there, A plus B and carry also there. So how many inputs are there now? There are 3 inputs are there. So here also 2 bits of sum and the previous carry. Previous carry means 1 plus 1 is there 0 and the carry is also there. Now 3 we have to add. So if half adder means 2 inputs are enough, but carry is there, we have to add carry also. But for this purpose I am using full adder, means previous carry also adding to this present value. So that is a full adder. Digital circuit that generates the arithmetic sum of 2 binary numbers is length is called binary number. So 2 binary numbers are there. So what is the length? With that is a binary number. Here interconnections of 4 full adders to provide a 4-bit binary adder. Here every full adder I am taking 2 inputs and 1 carry. So the output is added to, the output carry is added to the next value. 1 0 1 1 0 1 1 example. Here it is 1 example, it is B. 1 plus 1 here 0 and is it any carry? Yes, 1 plus 1 equal to actually 10, that is the sum value and it is a carry value. It is a carry and it is a sum value. So now I have to add 1 plus 1 plus 1. So 3 inputs are there. So previously like this, A equal to 1 and B equal to 1. Now A plus B, 1 plus 1. So sum is a 0. Is it any carry? Yes, carry is 1. Now this carry is forwarded to here. Now example here, A1 equal to 1, B1 equal to 1. So 1 plus 1 and this carry value plus 1. 1 plus 1 10, 1 11. So 1 and carry value is 1. Here example I am taking here 1 1. So 1 plus 1 plus 1. Now how much? 11 carry. 0 plus 1 example. So 0 plus 1 1, 1 plus 1 1. Is it any carry? Yes, the carry is like this. So what is answer now? 0 1 1 0. It is the answer. So full adder is using for 3 inputs, that means 2 inputs and 1 carry of the previous value. That is a full adder. And here we are taking as a design of 4-bit. Here 1 2 3 4. I am taking the 4, S0, S1, S2 and S3. So 4-bit binary full adder with truth table. The AND bits of A and the AND bit of B are designed by subscript numbers from right to left with subscript 0 denoting by the low order bit. The carry and connected in a chain through the full adder. The input carry to the binary adder is C0 and the output carry is C4. The S output of the full adder generates the required sum bits. Here I am taking one truth table for the previous diagram. For this diagram, we are going for the truth table. Here, how many inputs are there? Now, suppose A equal to 0 and B equal to 0. Is there any? If there is no carry, that means A plus B plus 0 carry. Sum, is it any carry? No. Here, A equal to 0 and B equal to 0. If any carry will be there, that means 0 plus 0, 0. 0 plus 1, 1. Is it any carry? No. 0 plus 1 plus 0. How much? 0 plus 1, 1. 1 plus 0, 1. No carry. 0 plus 1 plus 1. 0 plus 1, 1. 1 plus 1, 10. That means sum equal to 0 and carry equal to 1. 1 plus 0, 1 plus 0. 1 and 0. 1 plus 0, 1. 1 plus 1, 10. That is 0 and carry equal to 1. So 1 plus 1, 10 plus 0. 0 and carry equal to 1. 1 plus 1, 10 plus 1, 11. Sum 0, carry 1. So here like this. A value, B value and carry value. These are added to the together. It is a sum value and it is a C out value. So it is a truth table about the 4-bit full adder. Another example, design a 4-bit adder subtractor with truth table. The subtraction of micro operation can be done easily by taking the 2's complement of AND bits and adding it to the AND bits. The arithmetic micro operations like addition and subtraction can be combined into one common circuit by including an exclusive OR gate with each full adder. The block diagram of a 4 adder subtractor circuit can be represented. So here I am taking A, B, 2's complement of the eigenvalue. So mostly in the subtraction, mostly perform 1's complement or 2's complement. For majorly for subtraction, we are using 1's complement and 2's complement. So here I am taking the arithmetic micro-operation like addition and subtraction can be combined into one common circuit, including an exclusive OR gate is suitable for subtraction of full adder, and it is a 4-bit binary adder subtract circuit can be represented. So in the previously we discussed full adder S0, S1, S2, S3. I am taking here 4 full adders and A0, B0, A1, B1 like this. So we are adding with subtracting value here. So 4-bit adder subtractor. And the mode M is the low logic 0 and the circuit acts an adder. When mode input is high, the circuit acts as a subtractor. Here we are using exclusive OR gate for the subtraction of input M and one of the input is B. And M is at low logic, B XOR 0 equal to B and B XOR of 1 equal to B bar and C0 equal to 1 I am taking here. Example I am taking design a 4-bit binary incrementer with a truth table. The increment micro operation adds one binary value to the value of binary variables stored in a register. For instance, 4-bit register has a binary value. Here I am taking one example 0110. With incrementing by the one value becomes, so incrementer means we are adding plus 1 here. So 0110 I am adding plus 1 here. So 0 plus 1 1 as it is 0111. So design a 4-bit incrementer with a truth table. How we are designing, we will see it now. And the increment micro operation is the best implemented by a 4-bit combinational circuit incrementer. A 4-bit combination circuit incrementer can be represented in the following block diagram. Half adder I am taking. So in the previous like this, so I am incrementing to the first LSB. It is the MSB. So this LSB I am adding rightmost one. I am adding plus 1 here. So here input equal to 0. I am adding plus 1. Input equal to 0. I am adding plus 1. So 0 plus 1. 0 plus 1. 1. Is it any carry? No. If carry will be there, it will be forward. If no carry means it will be not forward. So 0 plus 1 equal to 1. Sum is 1. If carry equal to 0, then if it is 1, 1 plus 0, 1. Carry 0, 0, 1 plus 0, 1. Sum is 1. Carry equal to 0. 1 plus 0, 1. Like this. So carry equal to 0. So all ones like this. Example it is I am taking. So a logical 1 is applied to one of the inputs of least significant bit of half adder and the other input is connected to the least significant bit of the number to the incrementer. It is a LSB and it is a MSB. First bit is a LSB, last bit is a MSB. And the output carry from one half adder E is connected to one of the inputs of the next higher order half adder. The binary incrementer circuit receives the 4-bit from A0 through A3, adds one of it and the generates incrementing out of S0 to S3. S2, S3. So the output carry C4 will be 1 only after incrementing the 1, 1, 1. If I am getting 1 means it is the 1, 1, 1, 1 output. And logical micro operations. Previously we discussed shift micro operations. Here we discussed here arithmetic like addition, subtraction, increment, decrement. So these are the examples. Now logical microoperations means we are going for the logical means logic gates. We are applying logic gates to the inputs. And or XOR, XNOR, like this. Logic microoperations are binary operations implemented on the bits saved in the register. These operations treated each bit independently and create the matched binary variable from them. Example, I am taking one example. Example 4. Perform exclusive OR microoperation with the contents of two registers R1 and R2 is denoted by the statement. So I am taking R1 and R2 with XOR is there. So we are performing XOR. What is the design and truth table we discuss. It determines a logic microoperation to be implemented on the single bits of the register supported that the control variable p equal to 1. Consider that each register has the 4 bits. Let the content of R1 be the 1010 and R2 equal to 1010 and 1100. So we have to go for it is a R1 value and it is a R2 value. We are going for the what is a logic microoperation we will discuss. The exclusive OR operation is performed to the R1 and R2 and stated above represents the logic. So R1 is applied and R2 is there. After the R1 logic exclusive OR R2, the output is 0110. So here the 16 microoperations are available. Here clear 0 tends to F means clear. If I am symbol like this, and it is called transfer of A, transfer of B, exclusive OR gate. This symbol is called exclusive OR, and this symbol is the OR. Complement is there, NOR, or complement is NOR, and it is a exclusive OR, and it is a NOR, and complement B is there, B bar, that is called a complement, and it is a complement of A. Now A, but complement of A means A bar. It is the NAND and all set ones complement. So it is example of microoperations with two inputs 00, 01, 10, 11. So the above diagram shows the truth table of 16 logic microoperations, and X and Y are the variables or registers of the inputs, and F0 to F15 are the outputs that occur performing the logical microoperations. I am taking here 15 logical microoperations are performing with the two input values. Hardware implementation in the logics. The hardware implementation of logic microoperations requires that logic gates to be inserted on each bit or pair of bits in the registers to perform the required logic function. Although there are 16 logic microoperations are most computers used, and or XOR, exclusive OR and complement, from which all other can be derived, and the one stage of a circuit that generates the 4 basic logic microoperations are there, and it consists of 4 gates and a multiplexer. Each of 4 logic operations are generated through the gate that performs the required logic. In the hardware implementation, majorly we are taking 4 gates. 4 logic gates are performing with 16 microoperations. With using 4 gates performing 16 microoperations. I am taking AND, OR, XOR and complement. I am taking only 4 logic gates but performing 16 microoperations. And with 4 logic gates, I have the multiplexer also I am using for this one. 4 logic gates and 1 mux multiplexer to perform the required logic. Example, construct a 4 into 1 mux with a suitable logic gate and 1 stage of logic circuit and also with functional table. 4 is to 1, and that means 4 into 1 mux, that means 4 inputs, 1 output. But here in the 4 inputs I am using 4 logic gates. For the 4 inputs, I am using 4 logic gates. I am getting only one output. What are the 4 inputs are there? But here switches are S0 and S1. Why? Because I am taking S0 and S1 here. Here I am taking 2 switches. That means 2 square. That means 4. 4:1. So 2 switches means 2 square equal to 4. 2 square means 2 switches, S0 and S1, and 4 logic gates. That means 4 inputs, only one output. So what are the 4 logic gates? AND, OR, XOR, complement. 0, 1, 2, 3. 0 means I am taking here AND, OR, XOR, NOT. So these are the logic gates I am taking as an input, and the output is one output. It is a 4:1 multiplexer using. So 4 logic gates and 1 multiplexer, and getting the output with suitable 2 switches. It is a logic circuit. 0, 0 AND gate, 0, 1. If executing 0, 1, OR gate is enabled. 1, 0 means XOR is enabled. 1, 1 means complement will be enabled. So 2 switches, 0, 0. So 2 switches means 2 square, 4 possibilities. 4 possibilities of inputs and 1 output. 0, 0, 0, 1, 1, 0, 1, 1. 0, 0 means AND, 0, 1 means I am taking here OR, XOR, NOT. So when I am giving 0, 0, AND gate is enabled. 0, 1 OR gate is enabled. 1, 0 XOR is enabled. 1, 1 means NOT gate will be enabled. Here another hardware implementation with 4 gates of 1 multiplexer, and the output is also a gate with switches S0 and S1, and the applications of logic microoperations. Logical microoperations are useful for manipulating individual bits or a portion of a word stored in a register, and they can be used to change the values or delete a group of bits, insert new bits values of a register. Okay, for manipulating and for changing the bit values or deleting a group of bits or inserting a bit, for these applications we are using logic microoperations. So there are so many types of logical microoperations with registers: selective set, selective complement, selective clear, mask, insert, clear. So selective set, we'll each one will discuss. Selective complement, selective clear, mask, insert, and clear. Each one will discuss. Example: construct a logic gate with functional table and 1 stage of logic circuit. It is the AND truth table or XOR NOT. Already we know that what is the AND here. So if I am taking 0, 0, what is output? 0. So that means what is output here? A and A into B. AND means A into B. Here I am giving A and B. A or B are the 2 inputs. What is output here? A into B. If I am giving 0, 0, that means 0 into 0, 0. If I am giving 0, 1, 0 into 1, 0. I am giving 1, 0, 1 into 0, 0. If I am giving 1, 1, 1 into 1, 1. So 0, 0, 1. 0, 1. OR gate, that means plus. So 0 plus 0, 0, 0 plus 1, 1, 1 plus 0, 1, 1 plus 1, 1. XOR means we are taking 0 plus 0, 0, 0 plus 1, 1, 1 plus 0, 1, 1 plus 1, 0. NOT gate means if I am giving 0, it will come 1, 1 equal to 0. If I am giving A complement. If I am giving B input, B complement. That means B bar. It is also called 1's complement. So it is a not truth table. Another example: perform the selective set operation with suitable inputs and registers. The selective set operation sets to the 1 bit in the register A, where there are corresponding 1s in the register B, and it does not affect bit positions that have zeros in B. So it is a 1010 A before and 110, that is a B logic operation. Here 1110 A after. Okay, and it is a OR micro operation can be used. So for this purpose I am using OR operation. Perform the selective clear. That means I am taking here the corresponding logical operation is like this. Okay, the selective clear operation 0, A only, where the corresponding B. For example, A equal to 1010, 1100 is a B. So what is the operation performing? A before and it is a after. So for these symbols already we know that in the tables we discussed. A, like the symbols I am calling as, it is a AND operation. It is a AND operation is performed. Okay. Perform the mask operation with suitable inputs and registers. The mask operation is similar to the selective clear operation, except that the bits A are cleared only where there are corresponding zeros in B. The mask operation is an AND micro operation that is from the following numerical numbers. So 0110, 1010, all zeros, all 1. So suppose I am taking here A before and the logic operation. So mask means if all zeros are there, exact opposite I am taking all ones. So 0110 means 1010. So we are adding together. Mask operation similar to the selective clear operation, except all A are clear only there are corresponding zeros in B. And mask operation and micro operation is seen from the following. And it is a mask operation with suitable inputs and registers. And it is a mask operation with suitable inputs like this. It is I am taking as a XOR. So these are about the micro operations of logical. So in the logical operations, how many types are there? Selective set, selective complement, selective clear, mask, insert and clear. So mask micro operations are majorly we are discussing arithmetic and logic operations. So in that micro operations, we are designing and implementing of a complex machine instructions. We are using micro operations, and also for data storing of more in one or more registers, and we are transferring the data from one register to another register. Majorly micro operations are two types: arithmetic and logical micro operations. So types of micro operations: register transfer micro operation, arithmetic micro operation, logical micro operation, shift micro operation. It is a arithmetic micro operation. What are the operations are majorly possibilities: addition, subtraction, increment, decrement and shift operation. It is a symbolic representation with a description of micro operations. It is a full adder block diagram and truth table, and it is a adder subtractor circuit diagram with truth table. These are the logic micro operations. It is performing of exclusive OR with R1 and R2 registers. Total 16 micro operations are performed with 4 logic gates. These are the X and Y are the inputs, and 16 micro operations with 4 logic gates. So what are the 4 logic gates? We will discuss here. That is the AND, OR, XOR and complement. That means NOT gate. We are performing with 4 logic gates. 4:1 mux with suitable logic gates of one stage of logic circuit. So here I am taking 4 inputs, 1 output. What are the 4 inputs? Means 4 different logic gates I am taking with the 2 switching. That is S0 and S1. It is a hardware implementation of logic gate and applications of logic micro operations with selective set, selective complement, selective clear, mask, insert and clear. It is about the truth table of AND, OR, XOR, NOT. 4 logic gates with 16 micro operations are performed, and it is the truth table of selective set micro operation. It is the selective clear, and it is a mask operation. It is a mask operation with the input registers, mask operation with inputs and output. Okay, thank you.
Like, share and subscribe. Hit the bell icon for more updates.